There we go. And we are back live. Everything seems to be plugged in and working appropriately. There we are. Oh my goodness. Oh, we're back. And it's February. Man, I haven't changed this thing. February. Hold on. There's February. Today, Wednesday. Someone back me up on that. Sweet. So, and today's the 3rd, correct? Okay, hold on. I got this. Wednesday, February 3rd. There we go. There's for the camera right there. I hadn't updated that since January. So that'll stay there. Good. Excellent. All right. And we're back. It has been the craziest school year. See, the thing is, like, you would think, like, oh, snow day. We're going to have a snow day. Nope, we're not going to have a snow day. We're just going to get more work done, apparently, or something along those lines. Although Sunday seemed to be the only day to actually, like, go out in the snow. Personally, I'm not a fan of going out in the snow. I prefer cleaning the snow, but that's just me. My kids enjoy it to the point of frostbite, but that's all. Whatever, that's their deal. I don't know. If you notice, I don't know if you don't know my glasses. You'll probably see this several times today, but my glasses might fall off my face no less than half a dozen times today because my daughter has broken them, and I'm waiting to get replacements. And this little, I don't even want to call it the ear thing. The ear thing on the glasses is like loose, so it just kind of like slides off the front like that. So whenever I like put my head down like that, it just tends to slide very easily. So you'll see that several times a day. I'm going to try and keep a running tally. Anyway, I want to jump right back into what we were doing. For those of you in the chat, I can see 7 so far. If you would, those of you in the chat, 9. If you would leave a comment in the chat section, whatever, just for my record, that would be fantastic. So I have that because I know a number of you went virtual for multiple weeks prior. Oh, there they go. Good. And if you would, ladies and gentlemen, I'm going to need those notebooks out and open. I miss going to cubing competitions. But if I go to a cubing competition, I'm going to get shown up by a 12-year-old. They're the ones that usually are the best. Let's see here. Flip that over. Click. There we go. And there we go. I'm going to have my phone on the chat. So again, if you have any questions, you'll be able to ask them in there, and that'd be fantastic. And then I'll kind of introduce what we're going to be doing once I can get this thing kind of open here. Come on, you. Or, not update. Come on. Goodness gracious. It'll load. Good. So today is February the 3rd. We made it past Groundhog's Day. You guys seen the movie Groundhog's Day? You have. So one of you has, at least. Okay. If you haven't seen the movie Groundhog's Day, go see the movie Groundhog's Day. It is the most unassuming science fiction film of all time. Just saying. See it. This is sampling, distributions, continued. I wanted to recap something that we covered last class, well, technically Monday while I was at home. I wanted to recover something just to kind of iterate a point and then kind of build upon that from there. So last class we talked about students experiencing stress. And I kind of want to touch upon not that topic exactly, but the formulas that we covered as a result of that. And I just trying to, there it is. I was trying to find, oh wait, no, there it is. I was trying to find the page with the formulas on it. This is what we wrote down last time. I'll zoom in on that. These formulas we wrote down last time. So you should already have this written into your notes, but I just wanted to leave this up here for a little bit because I wanted to iterate the fact that these formulas are not too far off from what we typically use for a normal CDF, and more specifically, these two over here. And I'll show you what I mean. I'm going to make up some numbers, so I really hope they kind of work out. But I'm ultimately going to be using those formulas when I get to the point that I'm going to make. So I'm just bringing this up. You've already copied this down. I'm going to remove this in a moment. Let's talk about IQ. Very basic topic. IQ, on average, is 100. So IQ mu is equal to 100. The way that they typically measure IQ stands for intelligence quotient. Basically, you take a test and they measure your mental age. They take your mental age and they divide it by your actual age. They multiply that by 100, and that's how you get IQ. So if your mental age is equal to your actual age, then that should be, well, that divided by that is 1 times 100 is 100. And let's say that standard deviation is 10. Now, I don't know what the actual standard deviation is. I don't. But just for the sake of argument, let's just say it's 10 so we can keep it simplistic. So then I ask the following question. You select a person randomly. What is the probability that person has an IQ of, I don't know, 125 or more? Question mark. Let me zoom in on that a little. There we go. Again, trying to avoid the glare. Oh, I should note this. Assume normal. Sometimes you will be faced with free response questions that literally say in the description to assume normality. And if they tell you to assume normality, then you don't have to go through assumptions and conditions. They've already done it for you. The assumptions and conditions for assuming normality, you would either have to see a histogram of the data points and confirm that it looks nearly normal and things of that nature. But if they tell you to assume normal, then you're kind of in the clear. How many people am I selecting in my sample? Just one. Now, I ask that silly question. I ask that silly question for a reason. You're just selecting a person at random. Back in chapter 5, when I first introduced to you the normal curve and everything that had to do with the normality, I would ask a question similar to this. You select a person, one person, at random. And what is the probability that that person's IQ was 125 or more? Well, we would calculate normal CDF, 125, comma, big number, whatever that big number ends up being, like 10,000, doesn't matter, comma the mu, comma the sigma, in order to get our answer. This is what we did back in chapter 5. Now, to do this calculate, I'm going to bring up my little calculator right here real quick. I should have opened this sooner because I just want to use the same calculator that you guys typically have on your Chromebooks. Come on, smart view thingy thing. There we go. Second bars, normal CDF, 125, comma, some big number, doesn't matter what it is, comma the mu, comma the sigma, paste that sucker. There we go. 0.0062 or some junk like that. Which should make sense because, I mean, if you know anything about IQ, having somebody with an IQ of 125 or more is actually a big deal. Now, you can be honest, have you ever taken some advertisement pops up on your computer saying, hey, take this online quiz to figure out what your IQ is? No? Weirdos. And then you're like, look, I got an IQ of 145. No, you didn't. You jerk. Like, getting an IQ of 145 is astronomical. Astronomical. There are not that many people on the planet. You guys heard of Mensa? You don't know what Mensa is? Hold up. Hold on. I'm too excited. Hold on. I can't even get to the right window. Mensa wiki. Mensa is the largest and oldest high IQ society in the world. Nonprofit, but you have to have an IQ that is in the 98th percentile or higher. Yeah, you have to have an IQ that's in the 98th percentile or higher. You know what? Let's figure that out. What are the chances that you would find someone who would qualify for Mensa? Okay, hold on. Still one person. So hold on. Okay. Zoom out. Here we go. So to qualify for Mensa, you need an IQ in the 98th percentile or higher. So I'm going to do an inverse norm of 0.98, comma. Now, again, I'm assuming a standard deviation. I don't know that this actually is the standard deviation. I'm just assuming the standard deviation, but I do know that the average is 100. So I just want to be very clear about that. My assumption of the standard deviation may be greatly off, but I believe it's somewhere in that range. Anywho, let's do this calculation. Nope, wrong one. There we go. Inverse norm. Let's see, 0.98, 100, 10. Keep it to the left. Paste that sucker. Here we go. That's an IQ of 120.54. There we go. 120.54. Which is not too far off from what I actually kind of did with the 125. So you need an IQ of 120.54 or higher. That's pretty crazy. That would be the top 2%. What I calculated here was 125 or higher, which would be the top 0.5%. But regardless, that's kind of cool. Hold on, let me go back here. Mensa. What's the highest IQ anyone's ever had? Hold on. Highest IQ. I just type in wiki at the end of everything just because it just makes sense to me. Let's see. History, current test, reliability, blah, 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 blah. You're not going to give me numbers? Fine, you're not going to give me numbers. Highest IQ. No, get rid of the word wiki. Who is this kid? 198. All right, whatever. Okay, I'm bored with that now. Back to this. Okay. Now for my real question. This calculation was done if you selected one person, just one person. But now I'm going to randomly select a group of people. And I want you to think about that for a second. Here, I'm just selecting one singular person. And I'm trying to find the probability that I would get an IQ of 125 or higher with selecting that one person at random. But now I'm going to select a group of people. I'm going to select 26 people because there are 26 students enrolled in my AP Stat class. Now, obviously, if I just picked my AP Stat class, that would not be a random sample. That would not be a random sample. If I were to select 26 people, it would have to be a random selection. I would have to reduce bias as much as humanly possible. So let's just assume that I did that. But if I select a group of 26 people, I wonder what the heck is going to happen here. Hold on. Let's do the calculation. And then let's have the conversation. So, new scenario. I randomly sample 26 people. I randomly sample 26 people. What is the probability that their average IQ is 125 or higher? Question mark. Now, I want you to think about that question. I randomly sample now 26 people. And I want to know the probability that their average IQ is 125 or higher. Now, if I'm randomly selecting 26 people across the board, it should make logical sense that, well, if I'm randomly selecting them, there should be some people with average IQ. There should be some people with a bit higher IQ. There might be some people with lower IQ. Mr. Markey, you're not making it easy to get that 125 or higher. I know. Let's see what happens. Normal CDF, 125, comma, big number. According to the formulas that I wrote down the other day, and I'll kind of bring those back over here. I'll bring those back right here. There are the formulas that we wrote down the other day for quantitative data. The mean of the sample would remain mu. It would remain 100 for this example. But our standard deviation for the sample changes. Our standard deviation for the sample is going to change by being divided by the square root of 26. Let's see what happens here. This is going to stay 100. Oh, there go my glasses. And this is going to be 10 divided by the square root of 26. Now, one might ask, what is going to happen when I do this calculation? Dividing by the square root of 26 is going to reduce my standard deviation. It is going to reduce my variation. It is going to make the numbers a bit more consistent with each other. Less spread, less variation because of this altered standard deviation. And the reason why that happens again is because of the sample. So let me go to my calculator. And here's exactly what I would type in. By the way, what I wrote down here is exactly what I would write down. And then I would go to my calculator, and this is what I would type in. Normal CDF, 125, big number, 100. And I would type it in exactly as I see the fraction on my paper, 10 divided by the square root of 26. In some calculators, that number would automatically become a decimal. But in this calculator, it just stays the fraction that I typed in. But that's what I would have to change the standard deviation to. Oh my goodness gracious. What the heck is that number? If you not what the number is per se, but like how would you describe that number to somebody? Yeah. Impossibly small. Holy crap. Hold on. Let's see what I can write down here. This is 1.7 times 10 to the negative 37th power. Now, to be completely honest here, impossibly small is a great description. This number is essentially zero. Oh, there go my glasses again. When I say essentially zero, I'm basically saying, well, the number clearly is not zero. It's like 0.00000000000000017. It's a very tiny number. But it's still a positive number because it represents a probability. But when I say essentially zero, imagine this. Okay, imagine flipping a coin. Have you ever met somebody who believes that they can flip a coin and have it land on its side like a jerk? It's not going to happen. The chances of that happening are so impossibly small that we consider the chances of a coin landing on its side zero. Oh, Ms. Markey, there still is some chance. Yeah, I know. If you flip that coin from now until the end of the universe. You guys ever watch The Twilight Zone? There's a Twilight Zone episode with a guy flipping a coin into like something on the street and it lands on its side. And then he gets like impossibly good luck. No? Okay, whatever. Yeah, I'm the only one who watches those. But this is essentially zero. Now, what this really means in context, is this. If I go out and I randomly select one person from the population, just one, I believe, what was the answer? 0.0062? Yeah. Which means I have a 0.5% chance of, if I randomly select one person, I have a 0.5% chance that they would have an IQ of 125 or higher. But if I go out and I select a sample of 26 people, remember what I said about those 26 people. Some of them have lower IQs. Some of them have higher IQs. A lot of them will probably have average IQs. But what ends up happening is, well, they all kind of just cancel each other out. The larger the sample size, the more likely that my sample average is going to be 100 in this example. So if I select 26 people, there's a much smaller chance that I would get that IQ of 125 or higher on average. And that should make sense. It is experimental probability approaching theoretical probability. In this case, experimental averages approaching the theoretical average. It's the same concept. It's very strange. Now, if I were to actually take a sample of 26 people, would I get 100 IQ right on the dot? No. I might get 101. I might get 95. I might get 110. If I take a sample of 26 people, there's no telling where that average IQ might end up being. That average IQ might be 100. It could be. But more often than not, it might be a little bit higher, a little bit lower, blah, 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 blah. But it's going to be surrounding that 100. It's all going to be surrounding that 100. Like it was, and I'm going to draw a little image right here. It's like let's say that 100 was right there. And then I found an IQ of 100, and then there's one a little higher, one a little lower, and then higher and lower. And then basically, if I were to stack all of these IQs from here's down to 95, and here's 105. If I were to stack them in such a way, like a dot or a thing, or a histogram, what ends up happening every time I take these samples, the more samples that I take, what shape does that take? Let me repeat the statement. The more samples of 26 people that I take, and I put on this little chart right here that I just made on a whim, what shape does that start to make? What is that? Cricket, cricket. I hear crickets. I can hear them pretty well, even though they're all dead in winter. Yeah, it's the normal distribution. Everything that we've been doing has been building up to the next couple of definitions that I have for you. Everything that we've been doing since September has been building up to the next two sets of definitions that I have for you. Let's write down the first one. Let's see. First, I have something for you called, quote, sampling error. Oh, can't see it. Zoom out. There we go. Sampling error. When I say the phrase sampling error, do not think of this as a mistake. A sampling error is not a mistake. It is not an accident. It is not something done, by mistake. I can't even think of another word for mistake right now. Let me write down what this means, and then I'll kind of give you a visual example to it one more time. Sampling error. The reason a sample doesn't match, oh, there go my glasses again, the expected value, there are my glasses again, it's not a mistake. But a natural variation we'd expect to see from one sample to the next. I'm going to repeat that. This is such a big definition. There are two big definitions that I want to emphasize to you, and this is one of them. I'm going to repeat this one. A sampling error. It's the reason why a sample doesn't match the expected value. Well, average IQ was 100. So if I took a sample, I would expect that sample to have an average of 100. Yeah, I would expect it to have an average of 100 too. But more often than not, it's not going to. It's going to be a little bit higher or a little bit lower. Maybe you might just get it right on the dot, but that's just by pure chance. But a sampling error is just a natural variation that we would expect to see from one sample to the next. Here's a basic example right here. Flipping a coin. I'll show the coin right there on the camera. There's the coin on the camera. Now, I would hope that we would all know, ignoring landing on the side, of course, that when you flip a coin, the chances of getting heads or tails are 50-50. So if I flip a coin 10 times, how many tails would you expect to see? Yeah, 5. If you flip the coin 10 times, you would expect 5. But if I actually flip the coin 10 times, let's see what happens. Hold on. Boom. Heads. 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 Tails. How many is that? 5 so far? Cool. That wasn't a flip. There go my glasses again. I really need new glasses. Heads. Tails. Tails. Heads. Heads. That was 3 tails. 3 tails out of 10. Is the coin broken? No, the coin's not broken. The coin is not broken. We would expect 50-50, but we just took a sample right there. We would expect 50-50, but we got 3 out of 10. We got 30%. Now, when I say I got 30% out of 10 flips, you'd be like, that could happen. Hold on. Check this out. I got 3 out of 10 when I expected 50-50. And you're like, yeah, that's not too bad. This is 30%. What if it was out of 1,000? I flipped the coin 1,000 times. And I got 30%. Is there something wrong with the coin? There might be. There might be. And I can actually prove that. Let's actually go back to one of the previous definitions that I gave you. Hey, by the way, when you heard me flip that coin, did anybody hear the little ping? Yeah, do you know why? Before 1982, pennies were made out of 90% copper, and copper makes a bit of pinging noise when you do it. After 1982, they started making them mainly out of zinc, so when you hit them on the ground, you don't really hear that pinging noise, it just sounds flat. The more you know. Anyway. Also, the penny from 1943 was made out of steel because they needed copper for the war effort. The 1943 penny is the only U.S. currency that you can pick up with a magnet. Let's go here. Check this junk out. Actually, you know what? I'm going to put this on paper first. Let me put this on paper first. Hold up. So, you flip a coin 10 times. What is probability of getting 3 or less tails? That's exactly what we just did. That is exactly what we just did. Now, the formulas that we need for this scenario, assuming normality, of course, but the formulas that we need for this are these 2 formulas on the left. We need an expected probability of success, the mean, which we know is 0.5, and we need a standard deviation, which is calculated by the square root of PQ over N. So, mu of P hat equals 0.5. Sigma of P hat equals the square root of 0.5 times 0.5 over 10. That's 0.5 times 0.5 over 10. Let me just do that real quick right here. 0.5 times 0.5 divided by 10, square root of that sucker. Oh, that's a terrible number. I'm going to have to do this. It's 0.158. 0.158. Now, remember what standard deviation actually is. Standard deviation is average deviation from the mean. Standard deviation is, on average, how you would expect things to deviate from that mean. In this case, the mu is 50%, which means if I flip the coin 10 times, or if all of you flip the coin 10 times, and I took all of your proportions, You got 4 out of 10. You got 5 out of 10. You got 6 out of 10. I got 3 out of 10. If I took the average of all of them, no, I would expect the average to be around 0.5. But if I took the average deviation, I would expect it to deviate on average by about 16%. Let me go to normal CDF. Normal CDF, small number, comma, well, I'm going to do 3 out of 10. I'll do 3 out of 10 because that's what I'm getting here. 3 out of 10 is a proportion. Oh, my glasses. On average, it's 0.5. Standard deviation is 0.158. Now, after I do this, I am going to do it with 1,000 flips. But think about this in context. Let me go back over here. Second vars. Come on, second vars. There we go. Normal CDF. Small number. Hold on, clear that. Negative, blah, blah, blah. Doesn't matter. 3 divided by 10. 0.5. Clear that. The square root, 0.5 times 0.5 divided by 10. There we go. All the proper numbers typed into their location. There we go. It's about a 0.103, a 10.3% chance. What I just did in front of you, flipping that penny, what I just did, there was about a 10% chance of that happening. Yeah, that makes sense. Getting 3 tails or less. There's about a 10% chance of that happening. That's not too bad. 10% is not that bad. That could totally happen with a fair coin. Absolutely. That's 30%. Getting 30% or less, 10% chance. But now let's change it. I don't want to do 1,000, by the way. I want to do 100. I'll do 100. What if 100 flips 30 or less? Question mark. What if it were 100 flips? Now, let me set this up right here. And then I'm going to ask you a question about the standard deviation. Notice what I just wrote right there. I didn't put in the standard deviation just yet because I wanted to talk about what this would be. There is a 10% chance of getting 3 tails or less given all of these parameters. What is going to happen to the magnitude of my standard deviation if I flip it 100 times? What is going to happen to that standard deviation if now I'm not flipping it 10 times, I'm flipping it 100 times? What's going to happen to it? What does that mean? It's going to get smaller. That 100 goes on the bottom of the fraction. It is going to cause that standard deviation to shrink. Because the more times that you flip the coin, the less variation that you would expect to happen. I'm caught on a cord here. So in this case, 0.5, actually, no, you know what? Let me calculate this over here. Square root of 0.5 times 0.5 divided by 100. All of a sudden, look at that standard deviation now. That standard deviation is smaller. That standard deviation is now down to 5%. Before, when I flipped the coin 10 times, the standard deviation was 16%, meaning on average, your results would deviate by about 16%. But if we all flip the coin 100 times, Now, on average, we're only going to be deviating by about 5%. That makes sense? Yeah, I mean, the more times I flip it, the closer you would expect I would get to 50-50. I might not be exactly 50-50. Maybe I might be 51% or 55% or 42%. But it's going to get smaller. Let's see what this does. Boom. Normal CDF. Okay, 30 divided by 100. I actually don't have to change that. I'm just going to put 0.30. The thing I really do have to change is that standard deviation because of the sample size. Oh my. I actually am going to write that number out for funsies. 1, 2, 3, 4, 5. There we go. Click. There's that number right there. The more times you flip the coin, the less likely it is that you will be at 30% or less. The more times you flip the coin, the more samples that are taken, or the more trials that occur, the more evidence that you have that something might be up with that coin. If I'm flipping the coin 100 times and I'm still getting 30% tails, oh, my watch broke. Dude, everything is falling apart on me today. Gosh, just like my life. No, that was sad. I shouldn't say that. My life is awesome. There we go. Come on, you. Haha, I did it. I put it back together. The less of a chance that you have of getting 30% or less. And this probability actually shows me that if I flip the coin 100 times and I got 30% tails, now I have evidence to suggest that the coin is rigged. I have evidence to suggest that there's something wrong with the coin. I have evidence to suggest that that coin may not be a 50-50 coin. Up here, I didn't. Up here, I do not have evidence to suggest. Down here, I do. I may have mentioned this, like October. Maybe sometime in October. I really don't remember when I said this. But do you guys know or remember what the threshold is for whether or not you have evidence or you don't have evidence? I may only have mentioned this like once or twice total. I don't even think I wrote this down. The threshold is 5%. The threshold is 5%. This is more than 5%, so it's not evidence to suggest that there's something wrong with the coin. This is perfectly likely to happen. This is not very likely to happen. Now I have evidence to suggest that this coin is rigged. I have evidence to suggest that that coin is not a 50-50 coin. Evidence to suggest. It is now time for the moment I've been waiting for. It is now time for the fundamental theorem of statistics. There is a fundamental theorem of algebra. There is a fundamental theorem of calculus. There are a lot of fundamental theorems out there. You know that you cannot spell fundamental without mental. Fundamental theorem of statistics. You may see that abbreviated, but a lot of the time you may see it abbreviated not as FTS, but you may see it abbreviated as CLT. Because the fundamental theorem of statistics is also known as the central limit theorem. It just goes by a different name. That's all it really is. The central limit theorem, CLT. Now, what it is this. the sampling distribution of any mean becomes more nearly normal as the sample size grows. I'm going to repeat that and talk a little bit more into that. The fundamental theorem of statistics, aka the central limit theorem, basically comes down to this: the sampling distribution of any mean. It does not matter what that mean is. It does not matter if the original population distribution is not normal. It doesn't matter if something is skewed, bimodal, uniform. It does not matter. The sampling distribution of any mean becomes more nearly normal as the sample size grows. Now, what that means is this. I'll give you kind of an example with dice. Hold on. Where's my dice here? There's my dice. If I were to take this die and roll it and then ask you what is the probability of it landing on any one side, you would say, oh, it's 1 in 6. Yeah, I would agree. I would totally agree. You'd be like, 1 in 6. It's 1 in 6 for every single side. In fact, Mr. Markey, if you were to, draw a distribution of this, let's see. So there's 1, 2, 3, 4, 5, and 6. You would expect the histogram to look uniform like that. Absolutely, yes. I agree wholeheartedly. But keep in mind, you're only rolling it once. If you roll it once and then just take the result and graph it, the histogram would look like that. Yes, but that's only if you roll it once. What if you roll it twice and then take an average? What if you roll it 5 times and then take an average? What if you roll it 100 times and then take an average? The idea is that the larger the sample size grows, the more trials that occur within your experiment. If I rolled it 50 times and you rolled it 50 times and each and every single one of you rolled it 50 times and we all put our averages on the board, then the distribution of our averages would look nearly normal. That's the fundamental theorem of statistics. And it has to do with the averages. It's when you have a distribution of means. It's the fundamental theorem of statistics. Everything comes back to the normal curve. It's messed up. Okay. I'm going to pass something out to you guys right now. Yeah, I'm going to pass something out to you guys right now just because I want you to see a sample problem for this. For those of you in the chat, I'm going to post, there go my glasses. For those of you in the chat, I'm going to post the PDF of this in a moment. Just give me some time here. Here we go. There's 3 in there. 2 in there. 3 in there. 4 in there. Let's see here. Come on, internet. Google Drive. There we go. Sampling distribution practice. There we go. And PDF for today. Post. Excellent. There we go. Those of you in the live chat, I just posted this worksheet into the Google Stream so you can see exactly what it is that we are referring to. But I'm looking at this problem about near, this is hilarious. I did not anticipate that I would have something so perfect, but the nearsightedness affecting 12% of children. Hilarious. It is generally believed that nearsightedness affects about 12% of children. A school district gives vision tests to 133 incoming kindergarten children. Have you ever seen a young child in like preschool or kindergarten that has like glasses with like the little rubber band that goes around the back of their head? Is it not the most adorable thing you've ever seen? Just saying. Anyway, describe the sampling distribution model for the sample proportion by naming the model and telling its mean and standard deviation. Well, hold on a second. Where did that thing go? I literally, oh, there, my goodness gracious. This is how blind I am. I was just like, where did I put my glasses? And I literally put them like right in front of me. Okay. Where'd that other? I lost another paper. I don't know where that other paper went. Then it says to sketch and clearly label the model. Then it says, what is the probability that in this group over 15% of the children will be found to be nearsighted? Well, here's what it comes down to. The sampling distribution model and telling its mean and standard deviation. Because of the fundamental theorem of statistics, we can proclaim it to be a normal model. We can figure out the mean and standard deviation of the proportions, because even if you're doing proportions, you can still talk about means. For the sake of time, because I'm running a little short of time, let me zoom in on this, and let me fill in some of the key points here. Come on, focus there. There we go, cool. The mean of p hat should be equal to 0.12. The mean of the sample distribution should be 0.12. The standard deviation of p hat should be equal to the square root of 0.12, 0.88 divided by 133. If you're dealing with proportions, then you are going to be utilizing these formulas that we wrote down on Monday. If you are dealing with not proportions, but quantitative data, then you are going to be dealing with these formulas like we did earlier with IQ. You need to know what type of data you are using, and that will determine the type of formulas that you end up calculating. There's my calculator. Let's see, 0.12 times 0.88 divided by 133, square root of that answer. There we go. Our standard deviation should be approximately 0.028. Then it says to sketch and clearly label the model. Well, based on everything that we've talked about today, based on the fundamental theorem of statistics, based on all of these examples, I'm drawing a normal curve. Unfortunately, I may not be able to clearly label as much as I want to, because again, sake of time. But 0.12 is right in the middle of that normal curve. Going up each part of this normal curve, like we typically do, I'm going to be adding 0.028, which is the sample standard deviation. Let's see here. So 0.12 plus 0.028 is 0.148, 0.176, 0.204. Now remember, the distribution that I am drawing right now, the distribution that I am labeling right now, is based on a sample size of 133. If I change the sample size, I change the labels on the bottom of this curve. 0.12 minus 0.028 It should be 0.092, 0.064, 0.036. If I increase the sample size, those labels are not going to be as spread out. They're going to be a bit more consistent. If I decrease the sample size, put the sample size at, let's say, like 50, I am going to increase the variation that will take place. Now I'm going to skip the labeling again for the sake of time. Part C, what is the probability that in this group over 15% of the children will be found to be nearsighted? Normal CDF, 0.15, comma, big number, because, well, it's 15% or more, over 15%. 0.12%, or 0.12, I should say, I apologize. 0.12 is the mean, is the average, is the expected proportion. And 0.028 is the calculated standard deviation based on that sample size. That's what I would have to calculate. I'm just going to do that right here real quick. I have a calculator that's going to do that for me. 0.12 times 0.88 divided by 133. It is difficult without glasses. This should be approximately 0.144. There is approximately a 14.4% chance that we would see 15% or more of children in this sample to be nearsighted. It's a very specific thing. This chapter is the focal point of all of AP Stat because it brings together everything that we've done before and it sets up everything that we will do after. This is a very, very important chapter. Now, today's Wednesday. I have you again on Friday. I may throw something at you on Google Classroom. I haven't decided if I wanted to or not yet. We'll see. But it would most likely just be like a homework or something. But we'll get there when we get there. In the meantime, as I mentioned before, if you haven't commented in the chat, please make sure that you do. I have another class coming in approximately 15 seconds. So I got to sign off and create their stream. All right, bye-bye, everyone. Bye-bye, everyone. Stream, bye-bye. And there we go.